we'll look at TensorFlow 2.0 Essentials for Machine Learning. TensorFlow 2 Overview. In this video, we'll cover TensorFlow 2, what tensors are, eager execution, how we can visualize a graph, and automatic differentiation. Let's get started. Working with TensorFlow 2. TensorFlow is an end-to-end open source platform for machine learning. It has a comprehensive, flexible ecosystem of tools, libraries, and community resources that lets researchers push the state-of-the-art in machine learning, and developers can easily build and deploy machine learning-powered applications. TensorFlow Library is a free and open source software library for data flow programming, which models a program as a directed graph of the data flowing between operations, thus implementing data flow principles and architecture, and differentiable programming, where programs can be differentiated throughout, usually using automatic differentiation. This allows for gradient-based optimization of parameters in the program, often via gradient descent, across a range of tasks. It is a symbolic math library and is also used for machine learning applications such as neural networks. It is also used for both research and production at Google. TensorFlow was originally developed by researchers and engineers working on the Google Brain team within Google's Machine Intelligence Research organization to conduct machine learning and deep neural network research. The system is general enough to be applicable in a wide variety of domains as well, and it is one of the most popular libraries for machine learning with neural networks. TensorFlow provides stable Python and C++ APIs, as well as a non-guaranteed backward-compatible API for other languages. So to begin with, what is a tensor? So TensorFlow tensors are a generalization of vectors and matrices potentially higher dimensions. Internally, TensorFlow represents tensors as n-dimensional arrays of base data types, similar to the NumPy n-dimensional array. When we write a TensorFlow program, we mainly operate and pass around the TensorFlow tensor objects, which represents a partially defined data object that will eventually produce a value. In the TensorFlow program, we specify how these TensorFlow tensors link into a computational graph. We can then run the computation graph to get the output based on an input, and use differential properties of the graph to optimize for parameter TensorFlow nodes in the program. TensorFlow tensors can reside in GPU or CPU memory. TensorFlow supports a rich library of operations such as adding, mathematical multiplication, and also linear inverse matrix that consume and produce TensorFlow tensors. These operations also automatically convert to native Python data types too. So we can import TensorFlow as TF, and we can actually see what version we're running. In this, we're actually running 2.10, and we can actually start playing around with some native Python data types and actually performing add operations, square, and also some other reduce sum operations. So these actually turn the native Python data types into TensorFlow tensors and then run the TensorFlow operation on it. And we see here we're actually getting the immediate values out, and this is eager execution, which we'll define in a minute. So TensorFlow tensor has a shape and a data type. As we can see, in this case we have a shape of 1 and 2, and a data type of integer 32s. So tensors differ from NumPy arrays as they are immutable, and they can be computed and stored on the GPU or CPU. However, it is easy to convert from a TensorFlow tensor to a NumPy array, and TensorFlow automatically converts NumPy arrays to tensors. So if we have a NumPy array, and TensorFlow converts NumPy array to a tensor after a single operation, as we can see, we have a tensor after this operation. And also, if we use operating overloading too, so if we have an operator here, we'll also convert it to a tensor. Now we can easily convert back to a NumPy by actually having NumPy operations on a tensor. And how this actually works under the hood actually calls the NumPy method on the tensor to turn it back into a NumPy data type. So we can also index tensors the same convention as NumPy as well, using the index notation, and TensorFlow operations can be accelerated by parallelized to be computed on a GPU. By default, TensorFlow automatically decides whether to use a GPU or a CPU for an operation, copying the memory between them if necessary. So we can start with the tensor, and we can actually check whether we have a GPU on the system that's compatible with TensorFlow. In this case, unfortunately, my system isn't compatible with TensorFlow, but you can easily get a system to work on it. Also, a quick note here, you don't need a GPU-compatible device to run TensorFlow, because it can easily run in CPU or GPUs as well. So the TensorFlow has the same data type throughout for each element, And there are some special types of tensors, such as variable and constants, sparse tensors, and also placeholders. The data of a tensor is immutable, meaning that in a single run of the graph, the data doesn't change. Depending on the dimension of the tensor, we get the following. So for dimension 0 in TensorFlow, we get a scalar. 1 is a vector or a column matrix. 2 is a matrix, and 3 is a 3 tensor, and n is a n-dimensional tensor. So a variable such as the TF variable is the best way to represent shared state, and the value can be changed by running operations on it. Higher levels like keras use the variable to store model parameters underneath. So we can create a variable with TF variable and also TF zeros, very similar to the NumPy format. Now we can print them when we see we get zeros out the bottom, and we can also create scalars. And to assign a value to an already set variable, we actually use the assign method because the tensors are immutable. We can also explicitly read a value whilst using the read value as well. In this case, to read the value that we've set, which is 4. So eager execution. This is a very useful feature in TensorFlow 2.0. Enabled by default is eager execution, which is an imperative programming environment that evaluates operations immediately without building graphs. Operations will return definitive values rather than constructing a computational graph to run later. This makes it easy to start working with TensorFlow and debug models. This allows the use of Python's data structures, flexibility, how we can structure our code, and using Python control flow as well. This also supports GPU operations as well. So we can check whether we're actually executing eagerly by checking this TF executing eagerly method. And in this case, we can actually see it's true. So we are. So we can easily define some TensorFlow operations and actually see that the result is immediately returned. So if we define constants 2 and 3, we multiply them together, we expect the output to be 6, which it is. So we can also visualize the computational graph. So to do this, we have to put our function within a function or our operation, and then we have to use TensorFlow tracing by using this decorator syntax here. We'll go into TensorBoard in another video later on, but just quickly, this is how we set up logging, and then we can sample our function, and then we can actually trace it, and then we can actually use TensorBoard Visualizer to then have a look at the TensorFlow graph that it builds internally and uses. So this is a TensorBoard. We'll explain in detail how to use this in another video, but you can see the x and y variables and a mathematical operation to multiply them together. And you can see we can click on these and actually see some metadata about them as well. So we can see what label they are, what data type they are, also most input, what they actually connect to, and then we can trace up the computational graph, which kind of inputs it has and outputs. In this case, we have the identity and also identity nodes, and identity here is just multiplication by 1, and we're just using it to trace to then plot this graph. So automatic differentiation is a set of techniques to numerically evaluate the derivative of a function specified by a computer program. Automatic differentiation exploits the fact that every computer program, no matter how complicated, executes a sequence of elementary arithmetic operations, addition, subtraction, multiplication, division, and elementary functions such as exponential, log, sine, cos, etc. By applying the chain rule repeatedly to these operations, derivatives of arbitrary order can be computed automatically, accurately to working precision, and using at most a small constant factor, more arithmetic operations than the original program. So why do we care? So TensorFlow, obviously we can represent a data flow graph. We can also perform automatic differentiation on that graph, and we'll get into how that works now. So the chain rule for forward and reverse accumulation. So fundamental to automatic differentiation is a decomposition of differentials provided by the chain rule. For a simple composition, say of a function like this, we can split it up, and we can actually, by the chain rule, get this chain rule expansion. Usually two distinct modes of automatic differentiation are presented. So forward accumulation, or the forward mode, or reverse accumulation, or the reverse mode. Forward accumulation specifies that one traverses the chain rule from the inside to the outside. That is to compute first dw1 by dx, and then dw2 by dw1, and lastly dy by d2. While reverse accumulation has the traversal from the outside to the inside. So we can first compute dy dw2 and dy dw2 dw1, and at last dw1 dx. So more succinctly, forward accumulation computes the recursive relation of the following with w3 equals y, and reverse accumulation computes the recursive relation, which is the following: w0 equals x. Generally, both forward and reverse accumulation are specific manifestations of applying the operator of program composition, fixing the appropriate one of the two mappings W and Y. TensorFlow here actually uses the reverse accumulation. So in reverse accumulation, the automatic differentiation, the dependent variable to be differentiated, is fixed, and the derivatives is computed with respect to each sub-expression recursively. In a pen and paper calculation, the derivative of the outer functions is repeatedly substituted in the chain rule. In reverse accumulation, the quantity of interest is the adjoint, denoted by the bar W hat, and is a derivative of a chosen dependent variable with respect to a sub-expression W. So we can see an example here where we can actually compute the backward propagation of derivative values for a computational graph. You can pause the video and verify these by hand as well. So reverse accumulation traverses the chain rule from the outside to the inside, or in the case of a computational graph in the diagram, from the top to the bottom. The example function is scalar valued, and thus there is one seed for the derivative computation, and one sweep of the computational graph is needed to calculate the two-component graph. This is only half the work when compared to the forward accumulation, but reverse accumulation requires the storage of the intermediate variables, W to I, as well as the instructions that produce them in a data structure known as the Wengert list or the tape, which may consume significant memory if the computational graph is large. This can be mitigated to some extent by storing only a subset of the intermediate variables and then reconstructing the necessary work variables by repeating the valuations, a technique known as rematerialization. Checkpointing is also used to save intermediary states, and TensorFlow also supports checkpointing. The operations to compute the derivative using reverse accumulation are shown in the table below. Note the reversed order, where we start with the seed and then W4, 5, 3, 5, W2, 3, 1, and then W1, 3, 2, plus W4, cos 1. So the data flow graph of a computation can be manipulated to calculate the gradient of its original calculation. This is done by adding an adjoint node for each primal node, connecting the adjoint nodes which parallel the primal edges flow in the opposite direction. The nodes in the adjoint graph represent multiplication by the derivatives of the functions calculated by the nodes in the primal. For instance, addition in the primal causes fan-out in the adjoint, and fan-out in the primal causes addition in the adjoint. In terms of weight matrices, the adjoint is the transpose, and addition is the covector 1, 1, since obviously this expansion, and the fan-out vector is 1, since, and a unary function of y equals fx in the primal cases in the adjoint. So reverse accumulation is more efficient than forward accumulation for real functions, and especially when we have m is less than n in this case, and only m sweeps are necessary compared to n sweeps for forward accumulation. So reverse automatic differentiation was first published in 1976 by Seppo Limine, and backpropagation of errors in multi-layer perceptrons, a technique is used in machine learning, is a special case of the reverse automatic differentiation. In summary, we've covered TensorFlow 2, tensors, eager execution, visualizing graphs, and automatic differentiation.